All right. So at some point, make sure you bring up your homework and put that on the chair. So today we are going to start kind of the meat and potatoes of this chapter, which is aldol reactions. So when when I took organic 2, I thought that there was some guy called aldol and he came up with the aldol reaction, but that is not the case. Aldol is just a combination of aldehyde and alcohol. So there is no German guy named Rudolf Aldol or something like that. I don't know. Anyway, so unsurprisingly, these reactions are going to give us a molecule that has an aldehyde and an alcohol in the structure. All right. So there's 2 types of aldol reactions: aldol additions, which we'll do first, and then aldol condensations, which is just an aldol addition plus an extra step. Okay, so we know from the enolate chemistry that we just did previously that if we have an aldehyde like this is ethanol. If we have sodium hydroxide, then there's going to be an equilibrium between the ketone form or the keto form, because it's an aldehyde, so it's not really a ketone, and the enolate. If we look at the structures of these 2 molecules and we think about how they're going to react, just in a very general sense, the keto form is going to be electrophilic at that carbon, right? Because it's a carbonyl, just like, any other carbonyl compound. So it's going to be electrophilic at that carbon. The enolate, well, we know that has a resonance structure, and so it's not going to be electrophilic at that carbon because it's not actually electron poor. But instead, the enolate is nucleophilic, and it's nucleophilic at the carbanion, the C minus, the lone pair. So if we take the starting aldehyde, add in sodium hydroxide, we're going to have an equilibrium, at least of some sort. It's not going to lie very far to the right. So I guess you could say that it's the equilibrium is really more like that. But as long as you have at least a little bit of both of these present at one time, you can have a reaction between the nucleophile and the electrophile, because that's what nucleophiles and electrophiles like to do, react with each other. So, all right, we're going to form a carbon-carbon bond. Because both our nucleophile and electrophile are at a carbon atom. And so essentially what's going to happen is the nucleophile is going to attack the electrophile. That is going to create our carbon-carbon bond. And then there's going to be a protonation step we have to do. But that's kind of the main gist of the aldol addition reaction. So what does that look like? Okay. Well, we start with, I'm actually going to draw our aldehyde backwards because we're going to deprotonate it. All right, so we have an alpha hydrogen there that can be deprotonated. So now we've got our enolate. Now we have this equilibrium at the top between the aldehyde and the enolate. And so we've still got some amount of the aldehyde in our reaction flask. So we're going to connect the nucleophile of the enolate with the electrophilic carbon of, no, that's not what I wanted to do, of the aldehyde. And that's our carbon-carbon bond forming step. So additionally, what we have to do here, we can't have 5 bonds to that carbonyl carbon. So we're going to move some pi electrons up onto the oxygen. Okay, so this next part, you have to draw the molecule where the two molecules basically have attached to each other. This is probably the trickiest bit because you've got to make sure you have the right number of carbons and you have the right connectivity between all of the atoms. Okay, so what I've drawn so far is what used to be the aldehyde. And then we're going to connect the enolate there. And so it's going to look like that. Okay, so the new bond that we formed is right there in green. And so I think you can see that the two other carbons, there's the two that made up the aldehyde originally. And here's the two that made up the enolate originally. Okay, now all we have to do is just protonate the oxygen atom, and we're going to do that with the water that we formed in the first step. So we're going to regenerate hydroxide. And so as I do this, I'm going to draw it a little bit prettier. Like that. Okay, so as I mentioned, counting carbons is really important. So in the starting material, we have 2 carbons. It's a C2 molecule. We're going to react 2 of them together. So that should make a C4 molecule. And we can count the number of carbons in our product, 1, 2, 3, 4. And we do in fact have 4 carbons. So this molecule here is called a beta hydroxy aldehyde or ketone. In this case, it's an aldehyde. And this is the aldol addition product. Okay, so this process is, generally speaking, favored for aldehydes and disfavored for ketones. Remember, aldehydes are more reactive than ketones, and this is one of the instances where it's sort of really important because the ketones, if you want to do an aldol reaction or an aldol addition reaction, a ketone is not going to be a very good substrate for that. Okay, the way we actually end up drawing that is like this. So let's take this aldehyde. We're showing with an equilibrium arrow that the products are going to be favored in this reaction. And no, yes. That's the aldol addition product that we get. So let me do this. Yeah, let's see. Let's do colors. All right. So this can be puke yellow. And we have two equivalents of this. Sorry, I'm messing you guys up with moving stuff around, but so one of them can be puke yellow and the other can be magenta. That is a heinous combination, but okay, so puke yellow and magenta. Okay. And kind of shows up. All right, so there are the two molecules. One of them becomes, the oxygen becomes an alcohol, and the other, the carbonyl functional group stays the same. Usually, though, we just end up writing just that, like, that we have two equivalents of our aldehyde starting material.
How many exams do we need to know for like the equilibrium, which one's favored or?
Yes, but it's solely going to be up to whether it's aldehyde or ketone. So, for example, let's say instead that we're going to do an aldol with cyclohexanone. So another way we can write it is going to put each of the reagents or both equivalents of the cyclohexanone separately. So we're going to do sodium hydroxide again, but we have ketones as our starting materials. So that means the equilibrium is not going to favor the products. We can still write the product, but that equilibrium arrow indicates that the reaction is disfavored for ketones. And that is going to be the structure of the product. So we've got two of the molecules attached to each other. One of them comes from the enolate, one of them just comes from the carbonyl compound itself, in this case, the ketone. And we end up, in this case, with a beta hydroxy ketone.
So you just want to stay the same, the ones becoming an alcohol?
Right. Yep. So again, you could check your number of carbons. In this case, it's pretty easy because we have a 6-membered ring. So this is 6 carbons. This is 6 carbons. We should expect 12 carbons in the product. And yeah, we have 12 carbons. And then additionally, we need the hydroxy group to be in the beta position with respect to the ketone. So there's the carbonyl carbon, alpha, beta, kind of wish I had my laser, but and then the OH group is attached to the beta carbon, to the carbonyl. Okay, so in this reaction, you can do it for aldehydes, but for ketones, it's not practical to do. However, there is a reaction that works for both, and that is the aldol condensation, which is the same thing, just with one added step at the end. So remember that even though the equilibrium significantly favors the reactants for the ketone example, there is a little bit of that product that gets formed, and that ends up being important for the aldol condensation. Okay. Okay. So this is just going to be an aldol addition plus a dehydration. In that order, do the aldol addition first, and then we dehydrate the product. So we'd use ethanol like we did before, use sodium hydroxide, and then the key here is heat. Heat is a requirement for this reaction. First, we're going to get the aldol addition product. Do some more practice with predicting the products for this in a second, but we'll say that, okay, this is the aldol addition product, and I'm going to put it in a bracket because you can't actually isolate this product when you do the aldol condensation. If you add heat, I know that the term heat is kind of vague, and it's going to depend like exactly what constitutes enough heat to do the condensation versus the addition. Really just depends on the conditions and the specific reagents that you use. For example, in lab today, we did an aldol condensation, but you don't apply any heat. Turns out that room temperature is enough heat in order to get that particular set of reagents to do an aldol condensation. Anyway, so the addition product is not isolated, but instead what we're going to do is eliminate water. And the water is going to come from that hydrogen atom that's on the alpha carbon, or one of them, and the OH group. So we dehydrate, and that means we get a double bond in between those two carbons. Right there. So compared to the aldol addition product, do you think the aldol condensation product is more stable or less stable? Less? Any dissenters? So look at the position of the double bond. Okay, we have a carbon-carbon double bond on the right. And look at the distance between this carbon-carbon double bond and the carbonyl. What is the relationship between those two double bonds? Are they isolated? No. They're conjugated with each other. Conjugation means stability, conjugaft. So this is very stable, and we call this an alpha beta, no, alpha comma beta, unsaturated aldehyde or ketone. So let's do, I'll use this one as the example for the mechanism. So the first step is just the aldol addition reaction. Step 2 is dehydration, which in this case is the elimination of water. So here is our aldol addition product. So that's what we get from step 1. Then to start step 2, we just need to do a dehydration. And so that's going to be affected by hydroxide. So the hydroxide is going to deprotonate at the alpha position, like it does when you're making an enolate or anything like that. And the electrons will just sit on the carbon. Again, we're essentially making an enolate here. And now we just move the electrons toward that bond to create our double bond. And then the hydroxide group leaves. So we have our alpha beta unsaturated aldehyde. That OH has left. And then we've got the hydrogen that was on the alpha carbon. So, unlike just the aldol addition, the aldol condensation works for both aldehydes, or I should say works well for both aldehydes and ketones. So if we take acetophenone, a ketone with sodium hydroxide, the aldol condensation product that we get is not that. What am I missing? There we go. Yep. With the right number of carbons here. 6, 7, 8. Should have 16, 12, 13, 14, 15, 16. Very nice. See, I even have to check myself. Okay, so this whole section is all aldehydes reacting and becoming enolates and then reacting with themselves, or maybe reacting with a ketone, something like that. And as it turns out, chemists actually really do not like these reactions. And the issue is because they're pretty hard to control. So it's very easy to end up having sort of mixed aldol reaction. So if you've got several different molecules that can react in an aldol reaction, or even not a lot of them, just like two different ones. So say we have this aldehyde and that aldehyde, and they happen to be in the presence of some sodium hydroxide. what would the product of that reaction be? Well, turns out that there's four aldol addition products that you can get from that. There's four condensation products, one from each of the aldol addition products. And you're also going to get some polymerization. So have fun with that. Essentially, that means that if you're going to do an aldol reaction, doing it with two aldehydes like this is not a fantastic idea. You're going to get a bunch of different things. And so there's a couple of things that you can do to sort of make everything chill out. So you can for example, use an aldehyde like that, which has no alpha hydrogens. So that can't form an enolate, but it can act as an electrophile. So by doing that, you've eliminated one of the possible reaction pathways that that molecule can go on. So it can only act as an electrophile. Or you can use a ketone. Ketones react more slowly. And they only do aldol condensation reactions, not aldol addition. Well, of course, they have to do the aldol addition in order to perform an aldol condensation. But as mentioned up here at the top, if you've got a ketone, you have to go all the way to the aldol condensation product. So these reactants look familiar to anybody? This is the lab reaction. So if you use two equivalents of benzaldehyde, the benzaldehyde is going to be our electrophile, the acetone going to be our nucleophile through the enolate. It's acetone. And this is kind of a unique case where we have a double aldol reaction occurring. What happened is we've done an aldol reaction on the left half of the molecule, an aldol addition and then an aldol condensation, right? Because ketones have to do both. So we get our alpha beta unsaturated ketone on the left side. And then that reaction just happens again. We do another aldol addition and aldol condensation. And then we get the aldol condensation product on the right-hand side. Okay, so let's go through that in No, in some more detail. So we've got to have a nucleophile and an electrophile in order to do the aldol addition reaction. So how should I divide this up? Let's see. Okay, so we start with acetone. It's in the presence of sodium hydroxide. So we need to make our enolate. So we deprotonate there. Now we need our electrophile. And benzaldehyde is electrophilic. So we attack the electrophilic carbon of benzaldehyde. So the new bond, the new bond that we formed is right there. So you can see the benzaldehyde molecule on the left and the acetone on the right. And then water will protonate to give us the alcohol. Okay, so that was the first aldol addition reaction. Now we've got to do a condensation. And we do that by deprotonating at the alpha carbon again, just like we were going to make an enolate or something like that. Nope, sorry. Okay, so we deprotonate there, and then we eliminate the OH group to form our double bond. So we move these electrons to make the double bond, and then the OH group leaves. And so there's our carbon-carbon double bond. So this is not dibenzyl acetone, but just benzyl acetone.
One giant section.
It could be. I would probably break it down and make it a little more manageable because this is just the first half. And then I'm not going to draw it out. I'm going to let you do that. But then benzyl acetone undergoes another addition condensation with another equivalent of benzaldehyde. So what is that? 1, 2, 3, 4, 5 steps. So a total of 10 steps finally gets you to dibenzyl acetone. Which has benzyl acetone on one side and benzyl acetone on the other side. Okay. Let's do a little practice with, I'll leave that there for you. Predicting products, not necessarily doing mechanisms. So let's all right. Let's do the aldol addition of that molecule to itself. So if you like, you could draw it like that, or draw two equivalents. Hopefully you have a puke yellow pen and a pink pen for those, but what will the aldol addition product of those two be? Okay, so that's what the enolate should look like for one of them. Only one of them needs to become the enolate for the aldol addition reaction. So there's the carbon-carbon bond that forms. So there's the first half. It's going to be connected by our new carbon-carbon bond to the second molecule that used to be the enolate. So that carbon has two methyl groups attached to it. And then it's got an aldehyde group. So it looks pretty ugly, but you can clean it up a little bit by saying should probably protonate that oxygen, but I'll do that in a minute. Could also look like that.
You explain that further, because that is-
It is like, where did you come up with that? Yeah, I know. So my main suggestion for that would be that the mechanism is going to help you because okay, well let's try this. Okay. Why don't we take I'm gonna have to do it on here. If you got an iPad, this is super easy, but let's take that molecule and this molecule. So we know we're going to form bond between the alpha carbon of one molecule and the carbonyl carbon of the other one. That's a lot of words, but all right. So how do we do that? So let's say, let's pick them. So let's say we're going to use the carbonyl carbon of that molecule and the alpha carbon of that molecule. Orient them so that they are kind of close together-ish. Form your bond. And then we know that so we've got 5 bonds to the carbon at the top, right? And so that just means that we've got to replace that with an alcohol. So ugly as it is, that's correct.
I feel like, well, feel like when you check out the mold, yeah, when you took that out and you just said shift it across stick video, that makes sense.
Okay. It's kind of a feel thing, you know? No, that doesn't help, but yeah.
Because it just she kind of moved.
Yep. So yes, let's do. Okay, let's do two different molecules. Um, now let's do two of the same thing. Ooh. Okay. So we're going to form a bond between the carbonyl carbon of one of the molecules and the alpha carbon of the other. I'm going to flip this one. Do I want to do that? Nah, we'll just do this. Okay. Form that bond. And then convert one of them to an alcohol. It's correct, but ugly. So what we might do is say, all right.
Do you have to make it look for your kids?
It can stay ugly because it's the correct molecule. That's okay.
It's more simple.
So we've used two equivalents of the same molecule. If we had two different molecules, I think you now can see where all of those bazillion different products can come from. I'm not going to ask you to draw all of them. That would be evil. But do know that if you've got an aldehyde or two or three and maybe a ketone or something in your flask and you get some sodium hydroxide in there and it turns brown and slimy, this is what has occurred. A bazillion of these different, yes. No, if it does, now that you've said that, yours is going to turn brown. But no, did it turn brown for anybody this morning? No. Dark yellow, maybe, but mostly nice bright yellow. Yep. Okay, questions on aldol reactions? They're just the products just look weird. I struggled with it, so don't feel bad. I know that doesn't help. Okay, so afternoon, people, I'll see you in lab at 1:30.
Yes.
Yeah.
Okay, thank you.
Yeah, it's Tuesday, isn't it? Yeah. Yeah. Because there's only one more topic and it's really fast, so we'll have next time to do some review as well.
Okay.